Hello, welcome back. We are still in chapter 1. We are moving on to the next topic in chapter 1, which is homeostasis. This is probably the most important topic in chapter 1, other than learning all of your anatomical terms, which we'll see in the next video. So homeostasis is a very, very important concept in A&P. It is basically the driving force behind why your body does all of the physiology that it does, besides just pumping blood. How can we make sure that the blood that's pumping is maintaining all of the proper parameters of blood pressure and blood volume and exchange and oxygenation and all those things? So when we talk about homeostasis, if we break it up, homeo means same, homeo same, stasis same. So basically is a word that means same, or stable. So or same, stable. Anyways, homeostasis means you can maintain a constant internal environment even if the external environment is changing. So some really good examples of homeostasis that most people are aware of is your ability to maintain constant body temperature. So unless you're ill or in severe situations like hyper or hypothermia, you can maintain about your 98.6 or 37 degrees Celsius body temperature if it's 45 degrees outside, if it's 105 degrees outside, if you're in an air-conditioned building, if you're in a non-air-conditioned building. So except for those extreme situations, your body temperature stays the same, even if the environmental temperature around you is different. It's the same idea for almost everything in your body. We maintain normal blood oxygenation. We maintain normal blood iron. Again, with the exceptions of disease, because disease means you're out of homeostasis. We maintain normal blood glucose and blood sodium and blood calcium and blood potassium, blood pH, blood pressure, blood volume, muscle tone. All these things we are maintaining independent from the environment around you, or even other environments within your body. So your stomach maintains a pH of 2, even though the rest of your body is around a pH of 7 and 8. So even within your organism, you can have little microcosms of homeostasis outside of other places. So we're going to take a look at kind of the basic idea of homeostasis, and then we'll move into the two mechanisms, if you will, of how our body can maintain homeostasis with a few examples. So again, this is just a picture. It's an older picture I got off the internet. I like it. It's very basic. Your book has a slightly different visual to it, but the concepts are still the same. The parts are still the same. So in this case, it's showing that homeostasis is you're in balance. Right? So we're on this teeter-totter. The variable is balance. We're not going too high or too low in either direction. And so that puts us at homeostasis. And so our control center doesn't really have to do anything. However, if that goes in balance, right? So if this side goes up and this side goes down, we are no longer in balance. Maybe we have high temperature, high blood calcium, or high blood sugar or high blood pressure. Something is going out of balance, or it could be on the other side. It could be low, right? We could have low things. We could have high things. Remember, imbalances could happen in both high or low sides of the teeter-totter here. So this is what we call our stimulus, right? So that's very important. The stimulus is the thing that is being recognized as being out of balance. So we have to have mechanisms to recognize when things are in balance. That's homeostasis. And also when we have to have things to recognize when things are out of balance. That's out of homeostasis. So this stimulus is recognized by what we call a receptor. Okay? Sometimes it's called a sensor, but I use the word receptor. So it could be a temperature receptor if it's monitoring your blood temperature or your body temperature. It could be a calcium ion receptor if it's monitoring your blood calcium levels. It could be a pressure receptor if it's trying to maintain and measure your blood pressure. So whatever the stimulus is, we will have receptors to recognize that stimulus and be activated if needed. So in this relationship, the receptor picks up the stimulus. The receptor then signals that information to what we call a control center. And there's lots of different control centers in there. The big one, the main control center in your body, is your brain and spinal cord. their central nervous system. So the control center takes this information that's sent to it by the receptor and processes it. It's like, okay, so blood sugar, we'll talk with blood sugar because that's the example I'm going to use next. Blood sugar levels are too high. It's actually not monitored by your brain, it's monitored by your pancreas, but it's still the control center. So it's like blood sugar levels are too high, that's dangerous. We need to fix that problem. So then it will send a signal out to what we call an effector. The effector is the thing that can change the environment. So in this case, it might be gland secreting hormones, and the hormone's going to go and adjust the blood sugar level. If your temperature is too high, it might go and stimulate your sweat glands to release. So the control center in a temperature example is your brain sending the signal to your sweat gland, which would be the effector. The sweat gland sweats. The response to the effector is going to cool your body down, and then we'll be back to homeostasis. All right, so the major components of homeostatic control are the receptor, which picks up the stimulus, the control center, which receives that information and processes it, and then sends a signal out to the effector, which will then begin changes to try to bring you back into homeostasis. So those are the three parts of homeostatic control: receptor, control center, effector. Okay? And we have the thing that's going to trigger the whole thing is your stimulus, and the thing that's going to bring you back to regulation is your response. So these terms are also very important. So stimulus starts the whole thing, response is to try to get you back into homeostasis. All right, so there's a couple mechanisms that our body uses to maintain homeostasis. They're called negative feedback and positive feedback. The majority of your homeostatic mechanisms are regulated by negative feedback. There's only a few examples of positive feedback, but we'll show you examples, talk about all kinds of examples. So we're going to talk about negative feedback first. So this negative feedback, I'm going to focus on blood glucose levels. So first, before we kind of get to this cycle here, I'm just going to draw, this is kind of a graph, like a graph. So we have high blood glucose levels, which I think are like about 110. I don't know if the unit is milligrams per deciliter or something like that, down to about 90. So you don't have to worry about the units. I'm just putting context in our discussion. So if your blood glucose levels are anywhere between 90 and 110, you're in homeostasis. We don't have one number, like normal is 100. And if you're away from 100, you're going to be in a big trouble. That's not good. We have a range, which is normal, because your body would have a really hard time trying to maintain just one constant number. So when we are within a range, but we can go, up and down within that range, this is what we call dynamic equilibrium. So we are at equilibrium, but there's some dynamic to it. It's not a steady line, but it's a small enough range that our body is comfortable handling the ups and downs within that range. It's when we go outside of that range, either too high or too low, where your body starts having symptoms or signs of being out of homeostasis. All right, so whenever I'm in lecture, lectures usually at like 11:30 when we're in an in-person lecture. And I usually eat breakfast around 7 in the morning, or 6:30 to 7 when I'm getting ready. So by the time it's 11:30 or 12 when I'm lecturing over this on A&P day, my tummy's grumbling a little bit because I hadn't had any. I was in lab before. You remember when we used to have lectures in labs like regular? We'll get there someday. So let's say I had breakfast and then my body got me, my blood sugar is normal, but now I'm coming back down here. It's like 11:30, 12. Class doesn't get done till 1 o'clock. So I'm kind of on this low end. Maybe I'm even down here. And my body's like, something needs to happen because my blood sugar is getting too low. I'm going to back up because that doesn't match with my picture. So let's say I'm going to eat my breakfast here. And I like one of my guilty pleasures is I like sugary cereals. So like Cinnamon Life cereal or Cinnamon Toast Crunch or strawberry frosted mini wheats, which I had this morning. So let's say I have my breakfast of strawberry frosted mini wheats, and that's got quite a bit of sugar in it. So my blood glucose levels are getting high because it's all getting absorbed into my bloodstream. So here's my stimulus, right? rising blood glucose levels. So I have receptors all throughout my body recognizing how concentrated the sugar is in my blood. It is going to send us, pick up by a receptor, and this is our control center, the pancreas. My computer's not letting me write very well. Center, there we go. Control center is the pancreas. It's not the brain in this situation. So receptors pick up my high blood sugar, send that message to my control center. My control center is my pancreas, which has cells that release a hormone called insulin. So insulin is the response. So it's kind of the message, since it's not a nervous system message. This is hormone that goes to the blood and targets my effector, which in this case is my liver and cells. I'm going to put liver and cells in here because all of your body cells respond to insulin. So when the insulin shows up to my liver and to all of my body cells, it's going to say, hey, there's a whole bunch of sugar in the blood. I'm going to absorb that and store it in the liver or take it into the cells. And what that does is it brings my body back to homeostasis, right? So as body cells take up blood glucose, the blood sugar levels decline. All right, so my cereal made my blood glucose go high. The response to the pancreas and the insulin means my blood sugar is back down and I'm within the healthy range, the normal range, so I am in homeostasis, okay? The reason why this is called negative feedback, not because it's bad in any way, but the key idea is your response, right, which is bringing blood sugar levels down, is opposite the stimulus. The root for negative is to negate, to oppose, to go against. So if your response is opposite, so if my response is to bring my blood sugar levels down, my stimulus was my blood sugar levels are high, my response is to go low. Now, if I'm hungry, if it's been hours and hours and hours and I'm going down this way, my blood sugar level is too low, it's the same type of thing, but instead of releasing insulin, your pancreas releases a hormone called glucagon, which tells the liver to release all of that stored sugar from the morning, and it brings it back up until I can actually eat more food. So in this case, here's the response to the stimulus, right? The stimulus was blood sugar is too low. The response is your blood sugar is going to go high. So throughout the day, depending on meals, you're going to be bouncing between the upper and lower limit of this homeostatic range. And that's negative feedback because you're always going to say, oh, something's too high, we got to bring it back down low. If it's too low, we got to go high. If it's too high, it's got to go low. So this is kind of that driving force behind this dynamic equilibrium. We're kind of bouncing between your upper and lower levels, but that's okay because that's normal. What we don't want to do, like for people who have diabetes, is they go up like this and they have no insulin, or their insulin receptors don't work in your tissues. And so here you're going way high into too high of range and there's no mechanism to get it back down. And that's where you can get some of the severe negative outcomes of diabetes. So this was negative feedback with blood sugar, but we could do the same thing with body temperature, right? So the map would be, or this graph would be exactly the same. So if we had body temperature, say 99 here, and like 97 here, it's a much narrower of a range, say with the units from blood sugar. But if we go too high, we're going to sweat and vasodilate, and we're going to cool our body down. If we get too low, we might start shivering and constricting our blood vessels. And so we're usually, staying pretty normal. This one's a really narrow range, so our body is very tightly controlling on our body temperature, but it's the same pattern. We get too high, we cool down, we get too low, we warm up, we get too high, we cool down, and so forth and so on. So all negative feedback mechanisms will kind of have this up and down pattern of maintaining homeostasis. Okay, so that's negative feedback. The mechanism is what we call positive feedback. Now, positive feedback is different in that instead of negating or going against the initial stimulus that took you out of homeostasis, positive feedback, the goal is to return to homeostasis. And the fastest way to do that is by exaggerating or accentuating the stimulus. So It seems counterintuitive, so let's work through a couple of examples to make it make more sense. So one of the examples of positive feedback that your body uses to keep you alive is to clot your blood. Or I should say the platelet plug response is the positive feedback mechanism. So we're going to begin with damage to the tissues, right? So trauma, yikes, damage to the tissues, and chemicals are released. So this is the stimulus. They're released from these little, from your damaged cells, right? So we've damaged the lining of the blood vessel, we've damaged the muscle of the blood vessel, we've damaged skin. Those cells release chemicals that attract platelets. So platelets are these little guys here. They're non-cellular little bits that have a whole bunch of chemicals. They're just like chemical sacs. So this is the stimulus, chemical releasing into the blood. So in negative feedback, you think, well, let's just reduce those chemicals. That should get us back to homeostasis. But that's not the case here, because in homeostasis with your blood, you are in homeostasis because your blood is within your blood vessels. We are a closed circulatory system. Keep that blood inside the blood vessels. That's where it needs to be. If you are bleeding, your blood is no longer staying within your blood vessels, and that's bad. So homeostasis would be to get your blood vessels from not leaking your blood out of your blood vessels. All right, so if you're bleeding, you are not in homeostasis. To get into homeostasis, we need to stop the bleeding, and that usually means repair or plugging of that damaged blood vessel. So the stimulus are the chemicals released from the damaged tissue. In positive feedback, to plug up that hole in your blood vessel, we need more chemicals. So those platelets they attach to the trauma, they attach to the damaged tissue. And when those platelets attach, they release chemicals. And more chemicals attract more platelets. And more platelets come and stick, and they release chemicals. And so now we have got into what's called a positive feedback loop, or almost like a snowball effect. So more chemicals attract more platelets, release more chemicals, attracting more platelets, which release more chemicals, which attract more platelets, and so forth and so on. You get the picture. And then what eventually happens is we get into this positive feedback loop, and what we end up with is enough platelets come and stop the bleeding. We're back to homeostasis, right? So we don't want to decrease those chemicals that are released at the beginning of the tissue damage, because decreasing chemicals would not allow the blood vessel to be plugged up. We want to increase the chemicals and increase them quickly, because we want that platelet plug to be formed and stop the bleeding. And on average, a platelet plug takes only about 30 seconds to form, if it's, depending on the size of the wound, obviously. But that's pretty fast. So you get your tissue damage, you get your chemical release, you get your platelets aggregating together, releasing chemicals, attracting more platelets, releasing chemicals, attracting more platelets, and then we get our platelet plug. And then we get what's called hemostasis, which is blood clotting, the actual, all of this fibrin clot. That's the next step after the platelet plug. But the plug is your initial ability to stop the bleeding and return your body to homeostasis, which is not letting blood leave your blood vessels. The other major example of positive feedback I want to talk about, I have to draw the picture because we don't actually have a picture and I'm not the best artist. So bear with me. So the example here is labor and delivery. So think of a mom who is 9 months pregnant. Is she in homeostasis? Ask a 9-month pregnant mom and she's not in homeostasis. So let's say this is her uterus and her baby is in the birthing position, right? So head down. Happy baby. And the umbilical cord, right? So in the uterus, this area here is called the cervix. There's my cat's tail. You'll see my cats visiting my lecture videos, so just get used to it. The mom also has a brain, right? So this is her brain and spinal cord. So in her brain, she has part of her hypothalamus releases a hormone called oxytocin. So oxytocin goes throughout the blood and it binds to receptors on the uterus. And what that does is oxytocin causes contractions. So I'll draw these arrows. Kind of the uterus is squeezing on the baby. And what that does is it causes the baby's head to push down on the cervix. So that's pressure. It's a pressure receptor, right? So there's a stimulus is pressure. The stretch receptor is the receptor, so it's picking up on that pressure. And what that does is the cervix goes and tells the brain to increase oxytocin, okay? So now this is the control center, so now we get more oxytocin. And what are we gonna get? Oxytocin triggers contractions. So we get more contractions, bigger arrows, we get more stimulus from the stretched and pressured cervix, which is going to give you more oxytocin, which is going to give you more contractions. You see this snowball effect? So eventually what happens is enough of these circulating oxytocin molecules get picked up by this receptive uterus, and the uterus contracts and contracts and contracts, so much so then that the baby's expelled. And that's those stages of labor and delivery. To get the mom's body back into homeostasis, because you can't gestate a baby indefinitely. So once the baby's born, then the mom's body can start working to get back into homeostasis. So we have blood clotting, we have labor and delivery. The other two mechanisms that we'll be talking about mentioning positive feedback is peeing and pooping. So bleeding, giving birth, peeing and pooping, which somebody said a joke the other day that sometimes those all happen at the same time for women when they're delivering their babies. Those are pretty much the only positive feedback examples that we're going to be talking about through the entire year of A&P. So more likely than not, if we're talking about homeostatic mechanisms, if it's not those four things, it's going to be negative feedback. So of all the things that your body needs to maintain homeostasis in, the majority of them, almost all of them, are done so by those negative feedback mechanisms, where if your response is up or your stimulus is up, the response is down, right? So this will be negative feedback. Where in positive feedback, if your stimulus is up, the response is to exaggerate it. But their goal, both of their goals, are to return the body to homeostasis. All right, so that's our discussion on homeostasis. Make sure you're comfortable with the control, kind of the components of homeostasis. So the stimulus, the receptor, the control center, the effector, and the response. And then make sure that you understand and can be able to describe or define or give examples of both negative feedback and positive feedback. Okay, so that finishes that. We have one more mini lesson for chapter 1, and I will see you then. Bye.